Welcome to the Hayart Touch channel.
India designs roughly 20% of the world's semiconductors, but when it comes time to physically print those designs onto silicon, the entire country draws a blank. They currently have 0 commercial-scale wafer fabrication plants. That is finally changing. Tata Electronics is building an $11 billion facility in Gujarat, Gujarat. To pull this off, the Indian government elevated its strategic partnership with the Netherlands, securing a direct agreement with ASML, the Dutch company that holds a near monopoly on the machines required to print microchips. But there is a catch. Despite the billions spent and the heavy diplomatic lifting, this facility will only manufacture chips in the 28 to 110 nanometer range. Look at this timeline. The 28 nanometer node debuted over a decade ago. Today, modern smartphones run on bleeding-edge 3 nanometer chips. India is spending $11 billion to catch a technology train that left the station in 2011. Tech headlines often treat semiconductor manufacturing like a race to the bottom, where a smaller nanometer size is the only metric of success. However, the industry categorizes anything above 28 nanometers as a mature node, and for many applications, these are the preferred choice. This exploded electric vehicle relies on one central processor, but requires dozens of mature node chips to manage batteries, sensors, and brakes. Add medical and industrial tech, and mature nodes drive billions annually. Yet production is concentrated in East Asia, risking massive supply chain bottlenecks. By targeting these nodes, India avoids a direct war against the massive R&D budgets of TSMC or Intel. Instead, they step into a market with guaranteed long-term global buyers. India is making a calculated entry into the most resilient and profitable tier of the global hardware market. Buying an ASML machine and pouring concrete does not instantly create a functional, profitable factory. The core industry hurdle is yield learning. You have to figure out how to get a high percentage of working chips from every single silicon wafer through constant, expensive trial and error. That is why the partnership with ASML and Taiwan's PSMC is critical. They are transferring process expertise, enforcing supplier discipline, and training a new generation of Indian engineers to navigate these cleanrooms. A physical wafer might roll off the line soon, but analysts expect it will take until at least 2029 or 2030 before this facility earns global commercial trust. The Gujarat fab serves as a national training ground, building the foundational muscle memory of a domestic semiconductor ecosystem from scratch. This single factory in Gujarat anchors a much wider diplomatic offensive. India is trading its vast market access for the specific resources and infrastructure required to run heavy manufacturing. Chip fabs require massive amounts of pure water. To sustain this industry, India secured Dutch engineering expertise for the Kalpasar project, aiming to create a massive freshwater reservoir in Gujarat. To guarantee the energy security required for uninterrupted production, India signed a pact with the UAE to store 30 million barrels in its strategic petroleum reserves. To support long-term power needs, India launched an innovation corridor with Sweden focused on advanced manufacturing and green hydrogen, water, power, and fuel. These agreements are the prerequisites for sustaining an industry as resource-hungry as semiconductor fabrication. India is ignoring the vanity race for 2-nanometer supremacy. Instead, it is methodically pouring the unglamorous concrete, both physical and diplomatic, to ensure it becomes an indispensable node in the global hardware supply chain.